Hello guys, this is Saurabh, EPH third year, and I'm here to give presentation on my topic, modulation and demodulation. So let's start. So here are the contents of this slide. First, we will discuss some basic terminologies, and we will discuss why modulation is required. We will also discuss what is modulation and demodulation, also its types and its techniques to achieve modulation and demodulation. So we all know communication is the process by which information is exchanged between individuals through some common system. In verbally, it's the language, and in written mode, it's usually the symbols. In physics perspective, communication is the transfer of information from one point in space to another point, and we need the help of technology to transmit information over long distance. So here is a block diagram of a communication system. We have the source, which is our input, which is fed into the transmitter, whose role is to couple the message onto the channel using high frequency signal. Then we have the channel, whose role is to provide the medium from transmission of signal. Modulator is also a part of transmitter, whose role is to encode the signal. Then the signal goes through the channel to the receiver, and receiver role is to receive the signal that was transmitted. And demodulator is a part of receiver whose responsibility is to decode the signal which was encoded by the modulator. So first, before going to know what is modulation and why and what are its types and techniques, first we will discuss the main thing, that why we require modulation. Our message signal that we spoke is generally of low frequency signal. So there is an length of antenna versus is wavelength of the signal relation, that is L should be greater than lambda by 4. Since our message signal is generally of low frequency signal, which means it corresponds to a high lambda, and high lambda corresponds to a high length of an antenna. So to make the antenna size of order of kilometer for message signal of kilohertz order, which is quite impractical. So we need modulation. Modulation eliminates this problem. Also, we need to reduce the losses during transmission. And since path loss is inversely proportional to frequency square, we need modulation to increase the frequency so the loss decreases. Also, we need to maximize the use of bandwidth allocated. With modulation, we can restrict the bandwidth so that we can maximize the use of bandwidth allocation. Now we will discuss what is modulation. Modulation may be defined as a process by which some characteristics of a signal called carrier is varied in accordance with the instantaneous value of message signal. These instantaneous value can be either amplitude or angle or frequency. Initially, we always choose carrier frequency greater than the modulating frequency, and the resulted signal is called the modulated signal. And if the carrier wave is continuous in nature, such type of modulation is called analog modulation, and there are two types. First, amplitude modulation, second, angle modulation. Now we will discuss the types of modulation, as one is amplitude modulation and the other one is angle modulation. First we will discuss amplitude modulation, and then we will discuss angle modulation. So what is amplitude modulation? In amplitude modulation, the maximum amplitude of the carrier wave is made proportional to the instantaneous value of amplitude of the modulating signal or the message signal. The envelope of the modulated carrier has the same shape as the message waveform, which was achieved by translating message that is appropriately proportional to the unmodulated carrier. So if we assume Ct to be the equation of the carrier wave, which is Vc cos omega Ct, and mt the message signal, equal to Vm sin m omega t, then the amplitude modulated signal is St equal to 1 plus Vm by Vc cos omega mt into cos omega Ct. Now here is a pictorial representation of an AM signal. As you can see, the thing in the solid black line is the modulating signal, and the thing that is represented with the dash black line, black curve, is the envelope of this signal. So here is a signal, and this is an AM modulated wave, and this is an FM modulated. As you can see from this that the shape of the waveform is similar in the amplitude modulated wave, but it is not in the case of FM. But in FM, the amplitude is conserved, while in AM, the amplitude isn't conserved. So we will talk about the frequency spectrum of AM. So using Prosophares' identity, YT, which is a modulated signal, can be written as a sum of three sine waves shown below. So as you can see from this equation, we have three frequencies. First is FC, second is FC plus FM, third is FC minus FM. And the frequency spectrum is given in this graph. As you can see from the graph, we have various frequency. The highest one being FC plus FM, followed by FC, followed by FC minus FM, 0, minus FC plus FM, minus FC, minus FC minus FM. The portion from FC to FC plus M is called the upper sideband, and the frequency region from FC minus FM to FC is called the lower sideband, and from FC plus FM to FC minus FM we have our bandwidth. Now we will discuss the concept of negative frequency. As seen in the previous graph, we can see that the frequency to the left of O, that is 0, all are negative frequency. So it is basically nothing, but it is due to the exponential representation of the signal due to Fourier transform, and it is sufficient if we only consider it as a replica of the positive frequency. The bandwidth of AM signal will be FC plus FM minus FC minus FM, which is equal to 2FM, and we generally keep frequency of the carrier wave greater than the frequency of modulating waves to ensure that the two sidebands do not overlap with each other. Now we will discuss a very important concept, that is modulation index. So modulation index is used to manipulate the amount of modulation required as per SA requirement. So in case of an AM system, modulation index is a measure of the extent of amplitude variation about an unmodulated carrier wave maximum amplitude. So here's the equation. We have max of xt, which is the match signal, upon maximum carrier amplitude, which is Vc. And if we take Vm to be the maximum of message signal amplitude, we can write it as Vmax minus Vmin upon Vmax minus Vmin, where Vmax is the maximum amplitude of modulated wave and Vmin is the minimum value of the amplitude modulated wave. And Vmin is equal to Vc minus Vm, and Vmax is equal to Vc plus Vm. Also, it is important to ensure that the modulating index is always less than 1 or to unity, so to preserve the envelope of the AM signal. Now we have seen modulation, and now we have seen the modulation, which is the encoding of the signal. Now we need to decode it. So we require demodulation. So demodulation is used to extract the original information from a carrier wave, and demodulator is a device used to perform demodulation. So we have two types of demodulators detectors. First is envelope detectors and the other one is square law detector. We will discuss envelope detectors in the next slide. So now we will discuss the envelope detector. So what do envelope detector do? Basically, it is used when large carrier is used as a carrier wave. So what it does is to extract the envelope of the AM wave. So as you can see from this figure, this is a circuit of the envelope detector. We have a diode which will act as a rectifier. Then we have an RC circuit here. We provide an input which is an AM wave, and this is the output. So it's a non-coherent type of demodulation because we don't require the knowledge of a carrier wave at the receiver end. Now we will discuss the working of envelope detector. ST is our modulated signal, which can be written as AC, which is amplitude of carrier wave, into 1 plus Ka MT. MT is matches signal and K is the amplitude sensitivity, multiplied by cos omega CT. Now if we assume Ka to be 1 by AC, then ST can be written as AC plus MT cos omega CT, which is and AC plus MT is nothing but this envelope. And this envelope detector only works if AC plus MT is greater than 0. In other words, when modulation index Mi is less than 1. And now we will discuss why it is important to have Mi less than 1. As you can see, when AC plus MT crosses 0 to the negative region, this means we have a modulation index greater than 1. And when this happens, as you can see at this crossover point, there is a 180-degree phase reversal. Now if we use the envelope detector to recover the message signal, we will have some distortion, which will be a problem. So it's very important to ensure that MI is less than 1 for envelope detector to work properly. Now here you can see this is a circuit of an envelope detector, and here is our AM wave. So what happens when AM wave is positive, this diode will act as a forward bias and will conduct. So and this will charge the capacitor. So the capacitor will charge to peak voltage, that is this point. And when the capacitor charges to its peak voltage, the voltage across the capacitor becomes greater than the voltage across this diode. So this diode will act as a reverse bias and hence will not conduct, and this will become an open circuit, and what's left will be an RC circuit. Since when this capacitor was charged, you can see the output across this capacitor is this upward slope, this one. And when the diode is in the reverse bias, the capacitor will start discharging through resistor, and it will discharge, and this output and then the output across the capacitor will be represented by this downward slope. And after some time, the voltage across capacitor will again become less than the voltage across this diode. So hence the diode will again be in forward bias and will start charging the capacitor to peak voltage, which can be shown by this upward slope. And again after some time the voltage across capacitor increases, so this diode becomes reverse bias, and again the capacitor discharges through resistor, which can be shown by this downward slope. And it will keep happening, and this type of waveform will be attained. This time in the yellow marker we can see the obtained waveform. Now this is our output after passing through the envelope detector circuit. Now we will use a low pass filter which will remove the ripples in this wave, and we will have such type of waveform. Now we will use a DC block capacitor to remove the DC part, and which will give us the message signal. So here is the working of an envelope detector. Now we will switch into a new type of modulation, that is the angle modulation. In angle modulation, the total phase angle of a carrier wave is varied in accordance with the instantaneous value of the modulating signal or message signal, while keeping the amplitude of the carrier wave constant. So here the instantaneous value can be phase angle or the frequency. So there are two types of angular modulation under such. One is the phase, second is the frequency modulation. And this type of modulation is also called non-linear modulation scheme. Now we will discuss phase modulation and frequency modulation simultaneously. So what happens in phase modulation is that the phase angle phi is varied linearly with the modulating signal or message signal xt about an unmodulated phase angle, that is omega c tc plus theta naught. And st is our modulated signal and can be written as AC cos omega ct plus kp xt. Xt is our message signal, and where kp is the phase sensitivity of the modulator. While in case of FM, the instantaneous frequency omega I is varied linearly with a message or baseband signal xt about an unmodulated frequency omega c. So st denotes our message signal and can be written as AC cos omega ct plus kf integration 0 to t xt dt. Xt is our message signal and kf is the frequency sensitivity of the modulator. Now we will discuss the representation of FM and pulse modulation signal. So an angle modulated signal in general can be written as st equal to AC cos capital theta t, where theta t is the phase of the angle and its instantaneous frequency can be given by 1 by 2 pi d by dt theta t. So and st, that is the modulated signal, can then be written as AC cos 2 pi fc t plus theta t. Now the instantaneous frequency can be written as fc plus 1 upon 2 pi differentiation of theta t. Now kp and kf are the phases and frequency deviation constant. Then phi t, which is the frequency deviation, can be written as kpmt for pm and 2 pi kf integration minus infinity to t mt dt for fm. Now if we differentiate phi t, we can get kp d by dt mt for pm and 2 pi kf mt for fm. But from this equation we can tell, by passing the message through a differentiator then through an FM modulator, we can get a PM modulated signal. So we can convert a PM wave to FM and FM wave to PM. So here is that this is the picture. This is a carrier wave, and this is our message signal. So this is an PM modulated signal. As you can see, the amplitude is constant throughout. It's only the phases which is changing the frequency, instantaneous frequency. While in case of FM signal, also the amplitude is kept constant, but it's the instantaneous frequency which varies at some point. So frequency is much higher in this area compared to this area. Now we will talk again about the modulation index in FM and PM. In FM, the modulation index is the ratio of frequency deviation to the modulating signal. That is MF equal to KF AM upon FM. And in this case, FM can be greater than unity. And for PM, we have MP equal to KP max of MT, and max of MT is amplitude of maximum amplitude, that is AM of the message signal. Now we have another term especially for FM, which is percent modulation, and which is the ratio of delta F actual upon delta F max into 100, where delta actual is the actual frequency deviation and delta F max is the maximum allowable frequency deviation. Now we will talk about the demodulation of FM. So FM can be demodulated by using the following method. First, we have the frequency discriminator circuit. What it does, it converts FM into AM with the help of frequency dependent circuit, that is the circuit whose output voltage depends upon the input frequency. Then the other one is the slope detector. The principle of operation of slope detector depends upon the slope of the frequency response characteristics of a frequency selective network. So we will now discuss slope detectors. So what does slope detectors do? They take FM as an input which is fed into a frequency selective circuit which converts it into an AM. Then we use the envelope detector which gives us the output. So an FM slope is basically a tuned circuit of capacitor and inductor where the center or the resonant frequency is greater than the carrier frequency. In this way, the frequency modulated signal sits on the slope of the response curve, which can be understood from the following graph. As you can see, this is a graph between voltage, slope detector voltage versus frequency characteristic. As you can see from this graph, this is the resonant frequency, this is the central frequency, this is the highest frequency delta F from the central frequency, this is minus delta F. So we have 2 delta F as our bandwidth. As you can see from this graph, the higher the frequency below the resonant frequency, we get the max voltage. So below the resonant frequency, voltage is directly proportional to frequency. So as you can see, this is a circuit of an slope detector. We have a capacitor, inductor, and this forms kind of a transformer. Then we have this tuned circuit, and we have finally the envelope detector. As you can see, this is an FM modulated wave. So what happens? You can see in this region there is a high frequency compared to this region. So you can see that higher frequency means higher amplitude. So we have an amplitude according to this graph, and as you can see, this amplitude is greater in comparison to this amplitude. So as we move forward, we have this area is of low frequency region, and low frequency from this graph means lower amplitude, and which can be shown in this region. That in the case of low frequency we have low amplitude, in the case of high frequency we have high amplitude. So amplitude is, and so frequency is converted to amplitude according to this graph, and through this we can get an AM wave which is then fed into this envelope detector circuit. As previously discovered, this envelope detector circuit will extract the slope envelope of this signal and will give us the output. So that's the slope detector working. So I would like to end here. So we have discussed what is modulation, what is demodulation, its type, and how to modulate, how to demodulate, and we also talk about some important concept like modulation index. So that's all from my side. Thank you.